Hey guys, welcome back to Pop 'em Up Chem. We're still on acids and bases, and today we're going to be looking at buffers. As always, comment below to suggest things, let me know how you feel, like, subscribe and hit the bell icon so you get notifications about the videos, share the content, share the channel, and check out our other channels. Timestamps and links are all in the description. Let's get on with some buffers. So in this video, we're going to be looking at the composition of buffers, how they're made, what salt hydrolysis is, and then we're going to look at some calculations. Firstly, as always, little refresh question just to get you started. Pause the video here to give yourself some time to do that. Okay then, let's go through that answer. Looking at our calculations then, just like we did in the previous video, we always want to write out our equation first and our expression for Ka. Then we just have to remember our assumption that the equilibrium lies over to the left-hand side, and because of that, the concentration given to us in the question is going to be that of our ethanoic acid, which is 0.2. They've given us the value of the pKa here, so remember if we want the Ka, then we're going to need 10 to the minus pKa, so that's going to give me a Ka of 1.74 times 10 to the minus 5. And now I've got that value, I can do that equals to H plus squared because my two are going to be equal over the 0.2. Then I'm going to do 1.74 times 10 to the minus 5 times 0.2 all square rooted. It's going to equals the H plus concentration, which is 1.87 times 10 to the minus 3. All I have to do then, minus log of that, is going to give me my pH, which gives me 2.73. pOH, even easier, 14 minus the pH, which is 11.27. Awesome stuff. Okay, let's start having a look at buffers then. So buffers are solutions that resist change to pH. Now we can make this in two different ways. We can take an acid, a weak acid, and the salt of its conjugate base, or just add the conjugate base in some way to the solution. And we can do that by either just adding the salt of that directly, or we can do a half neutralization reaction. So just a little reminder of what conjugates are. If we take a weak acid, then the conjugate base is that which loses a proton. So for ethanoic acid here, it would be CH3OO-, the ethanoate ion has lost a proton, and so therefore is its conjugate base. Now, a buffer is a solution that contains both the acid on the left-hand side and the conjugate on the right-hand side. So that would be an acidic buffer, a weak acid and the salt of its conjugate base. An example of a salt we could use to add to this solution to give that would be sodium ethanoate, for example. So we could take sodium ethanoate crystals, add them to an ethanoic acid solution, and then we would form this buffer system, this weak acid buffer system. An example of an alkaline buffer may be ammonia, and to form its conjugate acid, we would have the ammonium ion. So the ammonium has obviously gained a proton, so we need to find a way that we would add that ammonium to solution, so we could use an ammonium salt, such as ammonium chloride. So that has the formula NH4Cl, where you can see that we have the cation there. Okay, so now we know what they are. How do they actually work? Well, we've said before that a buffer is a mixture of an acid, so HA bolded here, and its conjugate base, at least for an acidic buffer. So we've got this system set up where we have a concentration of both something on the left-hand side and on the right-hand side. And so these two components are able to react with things that are added to the solution, and the equilibrium will shift accordingly. So let's first take an example of what would happen if we add an acid. So if we add more acid, that's more H3O+, then we can see that because there is a large reservoir, because there is a large amount of A- in solution, that means that we will force the reaction to go shift to the left-hand side. We will actually produce more of the undissociated acid and more water, shifting it to the left-hand side. And you can see how this acts as a buffer, right? Because what's happening, we're removing acid, from solution and we're making water. And so therefore this is neutralizing that change. And so this is how these systems are able to resist small changes in pH, because as we add H+, we form water. Now, we get a similar process with a base. So let's look at that. Here, we're going to add OH-. Adding OH- will react with HA, which will move to the right-hand side and form A- and H2O. Once again, showing that adding base will be neutralized, at least small amounts, and so therefore we can say that it would resist the change in pH. And basic buffers are going to work in a very similar way. So when we have the basic setup, we have the base reacting with water, which forms OH- and BH+. So we can see by adding base what will happen. Well, if we add base, then the base is going to react with that BH+, forming B again and giving us some water, shifting the equilibrium to the left-hand side. Once again showing if we add base, then we're going to neutralize that change by forming water. Conversely, if we add acid, the acid is going to react with our base, and that is going to form more BH+ and also some water. Once again showing that either with the base or the acid we are neutralizing, and at least for the additions of small amounts of acid or bases, we're forming more water and thus resisting the change in pH. Okay, let's do a couple of questions on that then. First question, define the term buffer. Pause the video here to give yourself a moment for that. Pop 'em up! Hopefully you got a simple answer, like a solution that can resist small changes in pH. Okay, next question. How can an acidic buffer be made? Pause the video here to give yourself some time for that. Pop 'em up! Hopefully you mentioned either one of the two methods, adding a weak acid and a salt of its conjugate base together, or the half neutralization of a weak acid. So the half neutralization of a weak acid basically works on the principle that the equilibrium of a weak acid lies over to the left-hand side. So what you do is you add half the amount of moles of base to half neutralize it, which will give you an equal concentration of your A- and your HA by shifting the equilibrium to the right-hand side. Okay, next question. Write an equation to show how a solution of sodium ethanoate and ethanoic acid can resist the addition of more acid. Pause the video here to give yourself some time for that. Pop 'em up! Okay, so you can write out the first equation, as in the overall equilibria for the dissociation of ethanoic acid if you wish. And here you'll see we want to write how this could resist the addition of more acid. So acid is going to react with the ethanoate ion and then form more ethanoic acid. That second equation showing how it would resist that change because it would remove the H+. You could have also written this with H3O+ and then shown it producing H2O as well. Both are perfectly valid. Okay, now we want to move on to describing salt hydrolysis and how this affects the pH of solutions. Basically, salt hydrolysis describes that once salts are dissolved in water, some of them at least, still have acid-base properties, and it's important to take these into account when we're thinking about how a solution may react. Now, there are 4 different systems. The first one we're going to look at is strong acids and strong bases. So this is things like sodium chloride. Now, why do I say this is strong acids and strong bases? Well, we can see that sodium from NaOH and Cl from HCl both derive from strong acids and strong bases. That means that these conjugates really don't want to bond with OH- and H+, and so therefore they're going to remain apart. And because of that, the solution will remain neutral if we have salts of a strong acid and a strong base. Moving on to our next type then, hopefully you'll see a pattern. If we take strong acids and weak bases, the salt of the strong acid still reacts in the same way. It doesn't interact with H+ and isn't involved in the system. However, now we have the salt of a weak base, and the salt of a weak base here, given by the ammonium ion, will give up its extra H+ and will therefore react with OH- to form NH3 and H2O, which will remove OH- from solution and therefore give us a basic solution. Now we can further apply those ideas in the same way if we have a strong base and a weak acid, or the salts of a strong base and a weak acid. Here we take the ethanoate ion and the Na+ ion. The Na+ ion being the salt of a strong base and so therefore will not interact with the water, whereas the ethanoate ion will happily accept the H+ from any H+ in solution, and because it removes H+ from solution, it will therefore make the solution more alkaline. Last but not least then, we have weak acids and weak bases. So this one, we have both ions in solution are happy to react with corresponding ions. So the ethanoate here will remove H+ and NH4 removes OH-. So these will be approximately neutral. The exact pH will obviously depend on the nature of the ions themselves, because they will have a different affinity for how much they want to bond with OH- and H+. But in general, they'll be roughly neutral. Let's get you trying some questions for that then. First question, what pH would you expect a solution of potassium chloride to have? Pause the video here to give yourself some time for that. Pop 'em up! Okay, we would expect it to be roughly pH 7 because we have the conjugate of a strong acid and strong base, K+ and KCl. K+ obviously coming from KOH and Cl coming from HCl, which is strong base and strong acid, respectively. In a similar vein then, what pH would you expect a solution of ammonium sulfate to have? Pause the video here to give yourself a moment for that. Pop 'em up! Okay, so here we've got ammonium sulfate, which is NH4,2SO4. Now the ammonium ion, the NH4+, is coming from the weak base, and the SO4,2- is coming from a strong acid. Strong acid will not interact as it had full dissociation, and so therefore the NH4 will remove OH- from the solution and therefore make the solution acidic. Last one like this then, what pH would you expect potassium thanoate to have? So pause the video here to give yourself a moment for that. Pop 'em up! Hopefully you realize that this would be higher than 7 because we have KCH3COO made of two ions, the K+ and the ethanoate ion. The K+ from a strong base and the CH3COO removes H+ from solution because it's the conjugate of a weak acid. Therefore, the solution will become basic. Awesome. All right, let's turn our attention to doing some buffer calculations. So here, what is the pH of a buffer containing 1 mole per decimeter of ethanoic acid and 1 mole per decimeter of sodium ethanoate? So the main thing we're going to do here is obviously after we write out our Ka, we're going to make two assumptions which are slightly different from the calculations we've made before. The first assumption we're going to make is that the ethanoate ion is equal to the concentration stated in the question for sodium ethanoate. So because of the very low level of dissociation of the ethanoic acid, we're going to make the assumption that all of the conjugate comes from the added salt. And we're also going to make the assumption that the ethanoic acid concentration itself is equal to that stated in the question. So let's have a look at what this looks like when we calculate it. So they give us the value of Ka, which is 1.74 times 10 to the minus 5. And then we're going to do equals 1, because we said, remember, the concentration given to us of the ethanoate ion, which is from sodium ethanoate, multiplied by H plus concentration, which is what we're looking for. Now remember, this is not going to be equal to 1 now. And that is all going to be over 1, which is the concentration of ethanoic acid. From here, we're just going to rearrange by multiplying through by 1, then dividing through by 1. Very nice, easy calculation here. So we get H plus is equal to 1.74 times 10 to the minus 5 multiplied by 1 over 1, which is, of course, 1.74 times 10 to the minus 5. And to finish off what the question was asking us, which is the pH, we're just going to take the negative log of the H plus concentration, which was 1.74 times 10 to the minus 5. Once we take the negative log of that, we get a pH of 4.76. So slightly different assumptions in these calculations, but really still using the same equations, still using the same techniques as we were before. So let's get you trying a couple of questions on this then. First question, what is the pH of a buffer comprising 0.5 moles of ethanoic acid and 1.2 moles of sodium ethanoate? Pause the video here to give yourself a moment for that. Pop them up! Okay, so we're using the same expression for K that we used in the previous question, and we're just plugging in our values. 1.74 times 10 to the minus 5 is going to be equals, and we're going to take our concentration of our ethanoate ion from the sodium ethanoate, so that's going to be 1.2 multiplied by the concentration of H plus, which is what we're looking for, divided by the concentration of ethanoic acid given in the question, which is 0.5, and then we're just going to multiply and divide through by 0.5, then 1.2, so we get 1.74 times 10 to the minus 5 multiplied by 0.5 divided by 1.2. That's going to give us our H plus concentration, which is equal to 7.25 times 10 to the minus 6. And then to get the pH, we're just going to do the negative log of 7.25 times 10 to the minus 6, which gives us a final pH value of 5.14. Awesome. So in this situation, you've calculated what the pH of the buffer would be if you added these things together. However, what you often do if you're making a buffer is you want to know how much you need to add to make a pH. So that's why we're going to look now at calculating the proportions of a buffer. So here we're going to look at what mass of sodium ethanoate we need to add to a certain solution of ethanoic acid to make the pH 5.7. We're going to make the same two assumptions that we already made, just reiterating them here, that the ethanoate concentration will be only due to the sodium ethanoate we added, and the ethanoic acid will be that stated in the question. I'll just write out the expression for Ka, so we've got that there for our calculation. Okay, let's get on with it. Okay, so the question gives us our values in the pH and the pKa. So I'm going to convert those in the calculations to concentrations and Ka. So I'm going to do 10 to the minus 4.76, which equals my Ka, is going to be equals to 10 to the minus 5.7, because remember, we want our H plus concentration to be equals the pH of 5.7. We'll then multiply that by the ethanoate ion concentration. And remember, that's the thing we're actually looking for, because we're looking at how much of that I'm going to need to add to make this solution, this pH, divided by concentration of the ethanoic acid, which is 0.4. I'm going to rearrange that to get my ethanoate ion. So the Ka comes out at 1.74 times 10 to the minus 5, which I'm then going to multiply through 0.4, divide through by 10 to the minus 5.7, which is 1.992 times 10 to the minus 6. Pop all that into the calculator, and that's going to equals my ethanoate ion concentration, which is 3.48 moles per decimeter. So now we know the concentration of ethanoate ion we need. We just need to work out how much of sodium ethanoate we're going to add. So we want to find a mass. So that's going to be moles multiplied by MR. And we need to know our number of moles. Now we need a concentration of 3.48 moles per decimeter. And we have a solution volume of 0.5 decimeters. So I'm going to do 3.48 multiplied by 0.5 for my number of moles. All of that multiplied by the molecular mass of sodium ethanoate, which is 82. That comes out to 143 grams. So it turns out I'd need to add 143 grams to this half-liter solution of 0.4 mole per decimeter ethanoic acid solution to make a buffer solution that had a pH 5.7. You should know by now, ain't nothing to it but to do it. So let's get you doing a question. What mass of sodium ethanoate should be added to 0.25 decimeters of 0.1 mole per decimeter ethanoic acid solution to make a buffer pH of 4.5? Pause the video here to take as long as you need. Pop them up. So as usual, I'm going to write my expression for Ka, so then I can just plug in my values to that expression and rearrange to find the concentration of ethanoate first. From the question, I can see that I've got a 0.1 mole per decimeter ethanoic acid solution, so that's going to be on the bottom of the fraction, and I've got 10 to the minus 4.7 Ka and a 10 to the minus 4.5 concentration of H+, multiplied by the ethanoate that I'm looking for, divided by that 0.1. I'll write those numbers out in standard form, and I'm going to get 1.74 times 10 to the minus 5 is equal to 3.16 times 10 to the minus 5 multiplied by my unknown ethanoate over 0.1 multiply through by 0.1 is going to give me 1.74 times 10 to the minus 4 divided by 3.16 times 10 to the minus 5, which equals 0.055 moles per decimeter. I then want to find out my mass of ethanoate, so I'm going to need my number of moles multiplied by my NMR. I find my moles by taking the concentration I found and multiplying it by the volume, and then multiplying the number of moles by the MR. That gives me 1.13 grams. Awesome, guys. So the important thing to remember with buffers is that you need to remember how a buffer system is made and how it can resist changes in pH, and those two key assumptions for our calculations. Thanks for watching, guys. Please remember, comment below, like, subscribe, hit the bell icon. Please share this video, share the channel, check out our other channels, and as always, practice makes slightly better.